So let's see, a couple of announcements. This Thursday at noon, there will be a senior seminar presentation. One of our students, Evelyn Sanchez, our TA, Jordan Lehman, and some you probably already know, Tanisha Mataya, will be giving their senior seminar presentation on, the title is Brainless but Smart. It's about electrical activity, but not in the brain. So that's on Thursday. A reminder that the lab practical quiz is this week. I sent out time assignments in an email, but I've also posted it to Moodle. A file that has the time assignments are on Moodle. There is an open review today. I'm actually going to make the cadaver available today starting at around 1 o'clock, even though I'm going to be in the cell phys lab across the hall. But the room will be unlocked and available for you to do review today at 1 o'clock. And tomorrow, start from 1 to about 5:30, and tomorrow from 2:30 to 5:30. Natalie? That's on my desk. Okay, so open review today, this afternoon, starting around 1, and tomorrow, starting at around 2:30. And then the practical quiz is on Thursday, starting at 1, but you have your time assignment. The quiz will be about a half an hour. It is timed, so it's a firm time. So don't be late. So let's get to work on talking about the liver, more about the liver, and then move on to the intestines. Okay, so liver. So what our goals for today are to review some gross anatomy of the liver and specifically talk about blood flow. We need to talk about both arterial and venous blood flow to and from the liver. We'll talk about the microscopic anatomy of the liver, and specifically focusing on bile production of liver and the intestinal absorption of fat, carbohydrate, and protein, peptides. So here's a slide that I think I put up last week. We're going to focus on the synthesis and secretion of bile salts for the digestion of fat. We're focusing on digestive system. So number one is the most important function of the liver that we'll be talking about today. But let's not neglect that there are many other important functions of the liver, including storage of glycogen and storage of carbohydrate as glycogen, storage of fat as triglycerides, and then conversion of those storage molecules into amino acids and glucose when the body needs fuel. We've talked about serum albumin, we've talked about angiotensinogen, we've talked about urea. Cholesterol is an important part of the structure of membranes, so it's an important thing for the membranes. And then there's some other things that I've crossed out that we don't even talk about. Clotting factors, destruction of red blood cells, and so that converting hemoglobin into bile pigments, and excretion of toxins and trace metals as hepatic clearance. So the principles of clearance that you learned about for the kidney also applies to the liver for the things that are cleared by the liver. Not everything is cleared by the kidney. But let's focus on we'll focus on bile salts today. So here's just a reminder of the gross anatomy of the liver, the right and left bile ducts, the right and left hepatic duct, right and left hepatic duct, common hepatic duct, common bile duct, because this is the cystic duct, the gallbladder. All of these are ducts that provide flow of bile and bicarbonate from the liver. When the sphincter of Oddi is closed, that bile backs up and fills the gallbladder. When there is fatty acid and amino acid in the intestine, that is to say, during the intestinal phase of digestion, that stimulates the endocrine cells in the intestinal wall to secrete cholecystokinin. CCK relaxes the sphincter of Oddi and contracts the gallbladder, squeezing a pulse of bile into the intestine to help with the digestion of fat. CCK also, as you know, stimulates the exocrine glands of the pancreas to secrete enzymes, enzymogens, and stimulates the duct cells of the pancreas to secrete bicarbonate. Well, it assists secretin's primary function to stimulate duct cells to secrete bicarbonate. Okay, so those are some things that we reviewed from last week. We need to talk about blood flow. And the blood flow to the digestive tract is complicated. So let's talk about it for a bit. And I gave you this slide, and so I guess I'll ask you to annotate this slide. Maybe I'll annotate it on the board as we talk about it. Okay, so here is the abdominal aorta. It's labeled there, but you may not be able to read it. Okay, so this is the abdominal aorta here. And coming off of the abdominal aorta are a number of arteries, but the one that we want to focus on is this one here, the celiac artery or celiac trunk. Let's just call it the celiac artery. The celiac artery is this tube right here. A major branch off of the abdominal aorta. The celiac trunk, celiac artery, branches into 3 branches. So here's one, here's the second, and here's the third, okay? So there's the branching of the celiac artery. One of them is the splenic artery. Goes to the spleen. But actually it also feeds the pancreas. It's called the splenic artery. This one, which does this loop-de-loop thing. So let's follow this one. This one has a branch that we're not going to pay attention to. It goes around like this. And comes all the way back like that. So this artery, it's got some branches. I'm just going to cut them off now. That artery is the left gastric. The left gastric artery. and it provides blood to the stomach, and specifically to the lesser curvature side of the stomach. So the stomach is served, the arterial blood that feeds the stomach, at least near the fundus, especially on the left, on the lesser curvature side, is fed by the left gastric artery. This one here is the common hepatic artery. So that one is labeled on the slide. That's the common hepatic artery, which then branches into three branches. One of them is the proper hepatic artery that goes to the liver. So the liver receives arterial blood from the abdominal aorta, celiac trunk, common hepatic artery, proper hepatic artery, and then hepatic arteries. Just call them hepatic arteries. It branches to a bunch of arteries that feed all over the liver. So the blood, abdominal aorta, celiac trunk, common hepatic, proper hepatic. Okay, so that's arterial blood to the liver. The other branch here, this one here, which is going to join into the left gastric, this here is called the right gastric. So the left gastric and the right gastric meet up where we draw the boundary between right gastric and left gastric doesn't matter. It's just one artery, really. So blood flows both ways, and then obviously enters capillaries, and then enters venules in the lining of the stomach. Yes?
So you said the abdominal aorta, the celiac artery, common hepatic artery, and the proper hepatic artery take blood where?
To the liver.
To the liver.
So let's do the same thing for the blood that supplies the lesser curvature of the stomach. Celiac artery, left gastric, or celiac artery, common hepatic, right gastric. The blood that serves the lesser curvature of the stomach is either celiac, right gastric, or celiac, common hepatic, I'm sorry, I said it wrong. Celiac, left gastric, or celiac, common hepatic, right gastric. Feeding the lesser curvature of the stomach. This third branch off of the common hepatic artery is called the I think it's called pancreoduodenal. I'm blanking. Let's say it's not important. No, let's not do that. Let's call it the pancreoduodenal artery. Oh, no, I think it's not pancreas. There's another one. This is the gastroduodenal artery. What's that? Which one is this third branch off of the common hepatic? Yeah, I'm pretty sure of that now. Gastroduodenal. And now, so it's disappearing behind the stomach here. There's the pylorus. It's disappearing behind the stomach, but coming off of the gastroduodenal is this artery here, which is called the right, clarify that a little bit. This one here, which is coming from the gastroduodenal, so maybe put a dotted line there to indicate where it's coming from. The gastroduodenal artery has some branches that we can't see in this image behind the stomach here, but it forms the gastroepiploic artery. And this is the right gastroepiploic artery. And it's feeding the greater curvature of the stomach. Okay? So the greater curvature of the stomach on the right side is fed by the right gastroepiploic artery. Over here on the left side, the splenic artery, I'm going to make it dotted because it's behind the stomach. The splenic artery branches. Some of it goes to the spleen, which is right here. So the splenic artery goes to the spleen, you can't see it, but there's a branch from the splenic artery that is the left gastroepiploic artery. So let's review. The right side of the greater curvature of the stomach is fed, arterial blood is fed by blood from the abdominal aorta, celiac trunk, common hepatic artery, gastroduodenal artery, right gastroepiploic. The stomach on the left side of the greater curvature is fed by blood from the abdominal aorta, celiac trunk, splenic artery, left gastroepiploic artery. There are some other ones, obviously, like this one up here, that I can't even remember the name of, that feeds the fundus. So I can't remember it, so you don't have to learn it. It might be extra credit if you bother to learn it. You're okay. So it's complicated, right? I said the blood flow to the liver and to the stomach is complicated, but we've just talked about it.
So the pathway that is the next episode is one see abdominal aorta and the celiac and the left gastric artery. That's the
Mm-hmm.
and the other one is the hepatic and right gastric artery.
Yes, except you left out one word, common hepatic. Abdominal aorta, celiac, common hepatic, right gastric, right gastric. Yeah.
The left gastroepiploic artery joined with the splenic.
The left gastroepiploic, yes, is a branch from the splenic artery. So let's follow the blood flow to this part of the stomach. Abdominal aorta, celiac, splenic, left gastroepiploic. And then, so blood is coming in both directions. So blood, remember, blood is not going to flow all the way like that unless there's some problem, right? Blood is flowing in both directions, and then flowing into these branches, and then flowing into the capillaries that feed the stomach.
So the entire curve down here is the gastroepiploid.
This is the gastroepiploic artery, and this is the right side, and this is the left side of the gastroepiploic artery. This is the gastric artery, the left side and the right side of the gastric artery. That's just arteries. When we're going to get to veins, and they're almost as complicated. I'm doing this in part because blood flow to the liver is going to be really important in just a few seconds. And blood flow to the stomach is important too, right? The stomach is an active organ. It does all that churning, it's producing all that acid. It needs arterial blood in order to get the oxygen necessary to provide the final electron acceptor in the mitochondrial electron transport chain in order to make all that ATP that the stomach needs to do its work of churning and acidifying the contents of the stomach. So it needs a lot of arterial blood. And then, of course, there will be venous blood to drain all that arterial blood and to collect whatever absorbed, water and other material that might actually be absorbed through the wall of the stomach. Blood flow is important for the digestive system. And remember, when we talk about blood flow, we're really talking about the cardiovascular system. So we're looping all the way back to the beginning of the course, which is something that I'm liable to do to you, with you, on the final exam. Questions about this? Okay, so let's do the same thing. I'm about to erase all the green and talk about venous blood flow for a minute. Because the reason we have to go to veins right now is that the liver receives venous blood from the intestines. So the intestines are where most of the nutrients that we absorb from a meal are absorbed. Those nutrients go first to the liver. The liver gets first crack at all those nutrients to store it as glycogen or convert it into the things that the body needs. So the key veins that we need to talk about right now are here is the gastric vein. There's a left and a right side, but we're not gonna focus on that. So let's not worry about left and right. I gave you this one as a hard copy, right? So you can cross out left and right and short, and just remember that there is a gastric vein that combines with the inferior mesenteric vein from the intestines.
Isn't that the splenic vein? Then the gastric veins are a little bit more to the left.
Oh, you're right. I screwed this up. Okay, let me do this again. Here, this loop-de-loop thing is the gastric vein. This one is the splenic vein. This one that merges with the splenic vein is the inferior mesenteric vein. This one, so the gastric vein drains the lesser curvature. The gastroepiploic vein drains the greater curvature of the stomach. The inferior mesenteric vein drains the left side of the intestines, both the large intestine and the small intestine. So it's only showing the large intestine, but that's not the only thing it drains. It drains the left side of the small intestine as well. These veins join into this one here, this big vein, which is called the superior mesenteric vein. So all of this venous blood draining the intestines, full of nutrients after a meal, and we'll get to that mechanism in a few minutes, is feeding, going to the liver through the portal vein. The portal vein is the main vein that collects all of this nutrient-rich blood from the digestive tract, from the small intestine, large intestine, and stomach, and brings it to the liver. The portal vein. So the ones that I circled are the ones that you should know. Andrew?
So, we can know the difference from our inferior and superior mesenteric.
Yeah, you should know that the inferior is on the left side and the superior is further on the right side. Both of them drain intestines. And let's not be super worried about the part, you know from your quiz anyway, that the descending colon is on the left side. So most of the drainage from the descending colon is into the inferior mesenteric. And you know that the ascending colon is on the right side. And so you know that the drainage from the ascending colon is mostly into the superior mesenteric. You can figure that out. We don't, so this is saying that veins from both of these are bringing in veins from the jejunum and the ileum, from the small intestine. Wow.
You said that gastric veins drain the lesser curvature?
The gastric vein, yeah, this is parallel nomenclature. The gastric artery feeds the lesser curvature, and the gastric veins drain the lesser curvature. The gastroepiploic feeds the greater curvature. Gastroepiploic artery feeds the greater curvature of the stomach, and the gastroepiploic vein, should have circled that before, drains the greater curvature of the stomach. Zoe, did you have a question? Did I just answer it? Me?
In this picture, where does the portal vein ends and where does the superior mesenteric vein begin?
At this junction. When the inferior and superior mesenteric arteries join, which also includes the splenic, right? So at this junction, this is really the inferior mesenteric that joins in with the splenic here. When the inferior mesenteric and the superior mesenteric join, we now call it the portal vein. Okay, questions about remember what we're trying to do is talk mostly about the blood flow to the liver. And we have arterial blood and venous blood to the liver. Zoe?
So where does the gastric vein take blood
gastric veins will drain the stomach, and specifically the lesser curvature. Other questions? Remember, I've introduced the intestines already, but our main goal right now is to talk about blood flow to the liver. Arterial blood flow to the liver and venous blood flow to the liver. So now we're going to start to talk about the structure of the liver, which is, at the cellular level. Structure of the liver. It's got an interesting twist. So, here's the liver. You know the name of the ligament. Most of you got this right, the falciform ligament. Here is the hepatic artery feeding arterial blood to the cells of the liver. And here is the portal vein feeding venous blood to the liver. What is going to drain the liver after we mix this arterial and venous blood is the hepatic vein, which is going to drain into the inferior vena cava. Okay, remember, we've got hepatic arterial blood from the proper hepatic artery, and we have venous blood from the portal vein. Okay, so here, now we're going to go from the macroscopic to the less macroscopic. The liver is structured in these sort of arrays of cells called lobules. That's a word I want you to know. Lobule. A lobule is a collection of hepatocytes in a specific structure. Hepatocytes are the cells of the liver. Makes sense. I mean, everything having to do with hepato is liver. Hepatic artery, hepatic vein, and cytes are cells, hepatocytes.
Can you say a lobule again?
Lobule, a lobule is a collection of hepatocytes in a specific, well-designed, well-organized structure. Hepatocytes. You'll see in a minute. I'm just using the language right now. So these hexagonal arrays, each one of these is called a lobule. Okay, now we're zooming in on the lobule, and each one of these little boxes in the lobule is a hepatocyte. The lobules are fed with arterial blood, which is a branch of the hepatic artery. And venous blood, a branch of the portal vein. You already know that. Now we're getting into the microscopic stuff. The blood, so in almost all of the, in every other part of the body where the blood has started to make contact with cells, it's gone through capillaries, right? Capillaries are where blood makes contact with the cells of the heart and the cells of the muscle and the cells of the kidney, right? We always talked about a capillary endothelium. We don't have that here. There is no capillary endothelium here. The blood percolates, so the arterial blood percolates. Let me use a red one for arterial blood. Arterial blood percolates all around the cells without going through a capillary. And these are called sinusoids. The sinusoids are these microscopic spaces that the blood flows from the artery and from the branches of the portal vein around the hepatocytes. So the hepatocytes are bathed, literally bathed, in this tiny microscopic spaces that is filled with both arterial and venous blood. And at certain spaces, at certain points, it's a mixture of arterial and venous blood. Why do we have arterial blood going to the liver? The liver is metabolically active. It's doing a lot of work. It's using ATP. It needs oxygen to do its metabolic work. Why do we have venous blood coming to the liver? Because this is what's bringing the products of digestion to the liver. So the main point is that arterial blood and venous blood come in these branches of the vein, of the arteries and the veins, and then percolate through the hepatocytes that make up the lobule. And then that blood, after it percolates through the lobule, is collected in the central vein of the lobule. What does it mean? You know, a sinus is a space. So we have sinuses in our skull that are empty spaces where we can get, you know, we usually don't even think about them unless they get infected, and then it causes great pain and discomfort. So a sinus is a space. A sinusoid here is a tiny little space.
That holds the blood from artery and venous inflow.
That's right. So arterial blood and venous blood mixes in the sinusoid and percolates. So that's another word. Just, when you make coffee and you pour water over the grounds of coffee, the water is percolating through the little bits of coffee. That's percolation. When water is draining into the ground, into the groundwater, the water is percolating through the soil and then into the bedrock. And that's percolation also from a geologic perspective. There's no other word, I don't know of a good word to replace percolation. That's just the word percolate is the best word for how this blood moves through the liver lobule. Percolate. I suppose another good word would be perfuse. It perfuses the cells of the lobule. Okay, so we have brought arterial blood and venous blood. This is the main point. Oxygen-rich arterial blood and nutrient-rich venous blood to the liver lobules where the cells do their thing. And the thing that we're going to be focusing on is the production of bile. So here's an actual micrograph of a sinusoid. So here is the sort of hexagonal array. Hexagonal array around a sinus, around a lobule. So here is a branch of the hepatic artery. Here is a branch from the portal vein. Here is the blood percolating around, so the white spaces here are the sinusoids, and the pink spaces are the hepatocytes. The blood is percolating through, around the hepatocytes, and then going to the central vein. The central vein is going to drain into the hepatic vein, which is then going to go to the inferior vena cava, and then to the heart. So the words to know are sinusoids, central vein, branch of the portal vein, and branch of the hepatic artery. And you already know what venal and arterial is, so it's a tiny little branch. Okay? Okay. So now let's talk about bile. Bile is produced by the hepatocytes, among other things. Remember, the hepatocytes are doing a lot of things. That's why they need all that oxygen. That's why they're receiving all that nutrient-rich blood. But the thing we're going to talk about is the production of bile. So the hepatocytes produce bile. There's a separate plumbing structure, these tiny little tubes called canaliculi, I'm not going to circle that one, that form into small little ductules, but then are going to go and become the hepatic ducts. Remember, there's the right and the left hepatic duct that then become the common hepatic duct. Let's see if I can do this right. Which merges with the cystic duct, which becomes the common bile duct, which is going to bring bile to the small intestine. So that's where this is going to go. This bile is going to go into the small intestine. What's it good for? It's good for the digestion of fat. So that's where we're going now, is the digestion of fat. Oh yeah, so here's, did I get it right? Hepatic duct, common hepatic duct, marriages with the cystic duct to form the common bile duct, and we're going to the small intestine with the bile. So let's talk about what bile is and does, and then we'll take a break. Bile is a derivative of cholesterol. Bile is a derivative of cholesterol. So here's the ring of structure of cholesterol. You might even remember it from self-phys. And here's what makes it a salt. It's been modified to make it a bile salt. The point is, it is amphipathic. That's a word you should remember from self-phys. It's amphipathic. It has both hydrophobic or nonpolar areas and polar areas. It's an amphipathic molecule. It is essential for the solubilization of fat. So let's walk through this. So you've just eaten, I know it's gross, but let's just say let's do something that isn't gross. You've eaten a chocolate truffle, which is almost pure butter. Have you ever had one of those super rich chocolate truffles? I mean, they taste really good, but what's in it is mostly butter. And so you've just eaten a very tasty morsel of butter fat. Your body wants the calories from that butter fat, and so it got chewed up in your mouth, and all that delicious flavor got activated your brain, and there was some lipase in the saliva that helped start to break down the fat, and then it got into your stomach, and the stomach churning action and acid helped to churn up that globule of fat, that very tasty globule of fat, and turned it into into a globule, into something that is macroscopic, a glob of fat in your stomach. But then it gets into your small intestine, bile from your liver, which was stored by the gallbladder, is a detergent. It's a detergent-like molecule because it's amphipathic. And so it emulsifies the fat globule. It turns this macroscopic fat globule into something microscopic, an emulsion of fat and bile salt. And there's some lipid in there too. So we have solubilized the fat into something microscopic. And we call it an emulsion. Bile is essential for emulsifying fat, making microscopic particles of fat. So the fat droplet is emulsified by the bile salts. The lipase from the pancreas now has a large surface area of fat to work on, and it mixes with the bile salts and makes what are called micelles of the fat and the bile salt. So the lipase is chewing up, is hydrolyzing the lipid. The bile salts are continuing to solubilize the lipid, and we go from a microscopic emulsion droplet to an even smaller structure called micelles. And micelles are in equilibrium with free fatty acid. So here are the fatty acids and monoglycerides. This is a monoglyceride, this is a fatty acid that came from the action of lipase on micelles of fat. Monoglyceride fatty acids are in equilibrium with micelles. But there's a certain amount of it that is free. And it simply diffuses, because it's so nonpolar, it diffuses through, where are we now? This is the intestinal epithelium. What membrane is this? Apical. And it's got this highly folded structure. Apical membrane, it diffuses through this large surface area into the epithelial cell of the small intestine. The epithelial cells of the small intestine are specialized for then taking that monoglyceride and fatty acid and synthesizing it into a structure called the chylomicron. So the fatty acids and monoglycerides diffuse, are synthesized into triglycerides, and then mixed together to form chylomicrons. The chylomicrons are exocytosed. Self-is. And they are absorbed by, not by the blood here, and now it's really funny. This is lymph. This is a lymph vessel. Okay? So this is how we get the nutrients, calories at least, from fat into our body. Any questions about this story of how we get fat into our body here, into the lymph? The lymph is going to drain into a blood vessel. It's actually the left subclavian vein, but you don't have to know that. So the lymph goes to blood, and then the blood goes to the rest of the body. Well?
So you said the cell turn
Yes.
So they don't turn into the fatty acids?
Their fatty acids and monoglycerides are coming off and going on to micelles. So, yeah, they do come from. Remember, a micelle is a, so here's a lipid molecule, and here is a bile salt, and here's a lipid molecule, and here's a fatty acid, and here's another bile salt. This structure is a micelle. It contains a limited number of molecules, and some of these fatty acid molecules, and some of these lipids, and some of the bile salt is in equilibrium with just non-micellar, that is to say molecular, components. It's just like binding and unbinding. Okay, so here's a slide that just shows that cartoon of the apical membrane in the intestine is not so far from reality. Highly folded into microvilli to increase the surface area of the small intestine. And so here, and we'll stop here and then take a break. So here is the epithelium. What are these little hairs supposed to represent? The microvilli of the apical membrane. So this is the lumen of the intestine. This is a villus, a fold of the small intestine. Here's the microfolds, microvilli. The fat monomers, the fatty acids and monoglycerides diffused, were synthesized into chylomicrons, exocytosed, and picked up by the lymph structure, which has a name that I do want you to know, the lacteal. The lacteal drains into a lymphatic vessel, which is eventually going to drain into venous blood. So this is the structure of the intestinal villi, folds. The fatty acids and the monoglycerides can diffuse through this membrane.
So there's like no need to enter, and then they just freely.
They freely diffuse down their concentration gradient. There's no transporter, which is going to be different when we're going to get to carbohydrate and protein absorption by the intestine in just a minute. After the break, we're going to talk about how the intestine absorbs protein, amino acids, and how the intestine absorbs sugars from carbohydrate, and it's going to be different. There's going to be specific transporters. But in this case, it's simple diffusion and then exocytosis of the chylomicrons. Okay, a lot of material. I feel like, well, it's time for a break. Let's take a break, and then we'll talk some more. Expert in the mechanisms for how fat is absorbed. The cellular and molecular mechanisms for fat absorption. You know all about the liver, and you know all about bile, and you know all about chylomicrons, and you know about lacteals. You know cellular and molecular mechanisms for fat absorption. Now let's talk by the small intestine. And the mechanisms in the duodenum and in the jejunum and in the ileum are essentially the same. So we're talking about the small intestine overall. Now let's talk for a moment about the absorption of sugar, because you've eaten a meal that isn't just a chocolate truffle. You've eaten buttered toast or a baked potato with butter on it. It's got some fat, but it's also got some starch. Where did the digestion of the starch start? In the mouth, why? Mastication and salivary amylase. Don't forget mastication, it's important. You chew it, you don't just swallow it. Mastication, salivary amylase. Went to the stomach. Did pepsin do anything to the starch in the stomach? No. So we can just go through the stomach. We're in the small intestine now. The starch from the baked potato is in the small intestine. But now we have pancreatic amylase. Oh, there it is on the board. Pancreatic amylase. And other enzymes of the small intestine that are attached to the apical membrane. Maltase breaks down, so these are all disaccharides. So the amylase broke down the polysaccharide of starch down to disaccharides. And now these enzymes, maltase, isomaltase, sucrase, and lactase, break down the disaccharides into monosaccharides. The three main sugars that we have to talk about are glucose, which you know all about from self-phys, and two others, galactose and fructose. Those are the three main components of the starches that we eat and digest. There are others that I won't talk about. Fructose, glucose, and galactose. Galactose and glucose from the starch are first pumped into the epithelial cell. So remember, this is the microvillous structure, the apical membrane. A sodium-dependent pumping of galactose and glucose into the cytoplasm of the intestinal cell. It's not simple diffusion like it was with fats. It's a secondary active transport. And then the glucose flows into the interstitial space, which really is the lamina propria, that is fed by capillaries through a uniporter. This is a facilitated diffusion transporter that is it's passive transport. It's not diffusion, but it's passive transport. It's a uniporter. So this is secondary active transport using the sodium gradient to pump sugars into the cell, and this is sugars flowing down their concentration gradient through a uniport, facilitated diffusion transport. You don't have to learn the names unless you want to. It might help you to say, okay, this is an SGLT because it's sodium dependent, and this is a GLUT and it's not sodium dependent. If that helps you, that's fine, but you don't have to do that. What is this thing here? Sodium potassium ATPase. It's not showing ATP hydrolysis, but this is the thing that's creating the sodium gradient that is used by this secondary active transport. Fructose is the weird one. Fructose does not have a sodium-driven transporter on the apical membrane. It's got a uniporter on the apical membrane and then a uniporter on the basolateral membrane. So fructose absorption is just a little different from galactose and glucose. So this is how your body gets nutrients from starch. Amylase, these enzymes to break down disaccharides into monosaccharides. in some cases, sodium-dependent transport, in other cases, uniport into the cytoplasm of the intestinal epithelial cell, and then uniport into the lamina propria, where there's plenty of capillaries to pick it up. Some of you, you've probably all heard of people who are lactose intolerant. These are people who don't produce lactase. They don't have this enzyme. How many of you are lactose intolerant? There's got to be some of you. Yeah. Lactose, and yeah. Okay, I didn't mean to embarrass you. Some people just, Wendy Torrey, when she eats the pizza at biology colloquium, she always takes a pill which is actually lactase, because the cheese in the pizza disagrees with her unless she supplies her body with the lactase that her body isn't producing. So, people who are lactase deficient don't digest lactose, the milk sugar, and then the disaccharide isn't absorbed, stays in the lumen of the intestine where it isn't belonging, and causes, now there's a solute in the small intestine that should have been absorbed, and that's why it causes bacteria to grow in the small intestine. That's unpleasant. It causes gas to form, and it causes diarrhea, water to accompany that solute. So that's lactase, lactose intolerance, lactase deficiency. We call it deficiency, but it's actually the normal state of human beings. Human beings did not, well, the evolution of lactase was quite late in human evolution. It sort of coincided with the development of farming, dairy animals, cows and sheep and goats. Anyway, I don't know what's going on now. This is how you get sugars from starch, from carbohydrate into your body. Okay, let's talk about protein. The protein story is relatively simple. Okay, let's talk about protein. We chew it. So now we're talking about a piece of meat or something. Tofu. Let's go vegetarian. Tofu, pretty pure protein. We chew it, break it up in the mouth. In the stomach, pepsin starts to hydrolyze it into not polysaccharides, but polypeptides. Then it becomes some amino acids, some free amino acids, but in the small intestine, trypsin, chymotrypsin, and carboxypeptidase from pancreatic secretions digests the polypeptides even further. So now we have polypeptides that are broken down into amino acids. This slide is more complicated than it needs to be, because the point I want you to know is that there are sodium-dependent amino acid transporters on the apical membrane and amino acid uniporters on the basolateral membrane. Nothing else matters here. We don't need to talk about the peptidases. Peptides are broken down, polypeptides are broken down into amino acids, and we have a sodium-dependent pumping of amino acids into the cytoplasm of the epithelial cell, and then a passive facilitated diffusion uniport to bring the amino acids into the lamina propria where the capillaries are. Okay? So protein is probably the simplest of them all. The gastric peptidase is pepsin. The pancreatic peptidases are trypsin, chymotrypsin, and carboxypeptidase. Okay, so let's spend the last couple of minutes of this class talking about the anatomy of the intestines. So now we're going macroscopic. We've just gone microscopic. We talked about the microscopic anatomy of the intestines and how it absorbs fat, how it absorbs carbohydrate, and how it absorbs protein. Right? So those are stories that you should be familiar with. Okay, so you know what happens when you see a slide like this. I pull up Moodle, Google, and I cut and paste this. And we play the game. Volunteer. Start on this. Okay, call out a name and point to a button.
That'd be the
Ilium. This one here. Okay, appendix. Some of this is pretty easy. Which one? Duodenum. Show me. Secret. Okay, jejunum. Let's see if this is right. Nope, didn't like that. That's the duodenal jejunal flexure. So that one, we didn't study that one. It's just a bend in the duodenum at the junction between the duodenum and the jejunum. That's the jejunum. Yeah, that's the ascending colon. Okay, so I can do the rest. The iliocecal junction, the junction between the ileum and the cecum is the iliocecal junction. And you learned and you saw in lab that the mesentery is what provides all of that, well, it's fat and blood flow, both arteries and veins that supply and drain the intestines. Okay, so let's go to the PowerPoint and go to the next one and do this. Play the game a little bit more. Okay. Okay, anal canal. Yeah, I bet it's this one here.
With the appendix.
Yeah, it's still the appendix.
The ascending colon.
Yeah, that's still the ascending colon.
The ilium, or, yeah,
Ileum is this one here. And now we're looking, we've got a little window here into the cecum. There's the iliocecal junction from the inside. I'm going to do this one. Okay. Okay, they're getting trickier.
Is this the superior mesenteric artery?
this here, is that a superior artery? No, it's not pointing to anything that looks like an artery. What is that pointing to? There are people in the room who know because you labeled it on your quiz. Qua.
Tinea coli.
Okay, so it's either the tinea coli, it's either labeling the tinea coli, no, or the right colic flexure. It's the bend. It's labeling the bend. It's got a name, it's called the right colic or gastric flexure. That was not one of the required words, but it was an extra credit word. Okay, who's next? Okay, Natalie, can you?
That the superior mesenteric artery?
That is the superior mesenteric artery. Okay, so the tinea coli is the name of this sort of ribbon of connective tissue that surrounds the large intestine on both sides. This ribbon of connective tissue is called the tinea coli. Some of you actually labeled that one as well. And these bulges in the large intestine have a name called haustrum. So this is all in the coloring book, but it's not one of the, those are not words that are on your key list. They're not required, but they are worth extra credit, or they were on the quiz anyway. Epiploic appendages are these little fatty dongles off of the tinea coli, and the mesocolon is another name for the omentum. So, another set of games that you can play for the small intestine. I will ask you for homework to think about, so these are the arteries that feed the large and the small intestines. Some of these have names. Well, they all have names, but some of these are on the list. So take your key concepts list and map it onto here. You'll see things like the abdominal aorta, superior mesenteric, inferior mesenteric. Those are the ones that I see on here that are worth knowing. So prepare for Thursday, because Thursday we'll finish up the digestive system on Thursday, and then move on to sort of homeostasis. Trying to pull it together, reminding you of some key concepts from the whole course, which will come in handy for the final. So come prepared to talk about the arteries to the intestines and the veins. We've talked about them today, but we'll play the game on Thursday.